It's my great pleasure to introduce the next speaker, Jacob Tsimerman. Jacob received his PhD in 2011 from Princeton University, supervised by Peter Sarnak. And he was a junior fellow at Harvard before moving to his current post at the University of Toronto. It's been my great privilege to be a collaborator of Jacob's for about the last 10 years. Jacob works in analytic number theory, algebraic and arithmetic geometry, and Hodge theory. And he's achieved several spectacular results, notably on and around the André Grothendieck conjecture and algebraicity questions in Hodge theory. His work has been recognized by several prizes, including the Sastra Ramanujan Prize, Mathematical Council of the Americas Prize, and the New Horizons Prize. So Jacob will speak about the André Grothendieck period conjecture of a function field.
Thanks very much. Okay, is that good? Yeah, okay. Thank you very much. So, yeah, I want to speak today about sort of a functional analog of a very nice story that exists over the rational number, so sort of classically. So let me begin by sort of laying out the classical story, and then we'll move to a different setting. So what I want to start with is sort of ordinary transcendence theory. And the first thing I want to look at in the majority of what we'll be talking about this talk is periods. And so what are periods? Well, vaguely speaking, periods are just integrals of differential forms and for the purpose of the first part of the talk, at least the thing we most often think about, we'll talk about these things over Q. So vaguely that's what they are, and concretely what that means is your differential form should be defined over Q as well as the thing that you're integrating over. So some examples. If you look at the integral from 1 to n of dx over x, you get log. That's one of the things you're allowed to do. You're also allowed to take higher dimensional integrals. So a nice example is if you integrate, yes. Oh, sorry, I heard someone say my name. Over the unit square, dx dy over 1 minus x times y. Sorry, this is not the unit square. This is the unit triangle. 0 at most, x at most, y at most 1. You get zeta of 2. And you can replace the things inside here with sort of different algebraic functions of x and y. And you can replace the regions of integrations with much more general things, let's say like semi-algebraic structures over Q. And so the conjecture that I'll make more precise, but I want to start out just giving the yoga, is that all algebraic relations amongst periods come from geometry. Okay, so as an example to illustrate this principle, let's go to our logarithmic setting over here, and we have the relation log m plus log n is equal to log times log of mn. And let's try to explain this from a geometric perspective. Of course, it's sort of just rewriting things we already know in this language, but I think it could illustrate what's going on. So we'll let x be gm, so C star, if you don't want to think about algebraic groups. We'll let z inside x be the set of points 1 and n. Then we have a homology cycle inside X relative to Z, which is just the path from 1 to n, the sort of obvious one. And we have a differential form, dx over x. OK, so from this language, what we're doing is we're taking this differential form, and we're integrating it over this relative homology cycle. OK, now we have a map from x to itself, which sends t to m times t. And it sends z to m mn. And the pullback of omega under this map is equal to the integral, is equal to dx over x. So just omega again. And so what we conclude, based on these purely sort of algebraic maps, is that the integral from 1 to n of dx over x is equal to the integral from m to mn of dx over x. So then if we take this and put it together with this guy here, we can go from 1 to mn and you do this relation. So of course it's change of variables, the usual proof. But the idea is we obtain this relation based on purely geometric considerations. So as maybe before I actually move on, I'll just write over here. Most of the stuff is still extremely open in the rational setting. But we have a theorem due to, I'll put a few names here, Baker and Wustholz are the sort of most, I think, important ones. That if we look at logs of algebraic numbers, these are, we don't know they're algebraically independent, but they're Q bar linear independent. I'm so sorry? Oh, right. I always mess it up the other way, and so yeah. Sort of modulo the obvious relations. OK. So given this as our sort of prototype, we can now try to formulate this conjecture in full. And so to do that, let me introduce the period ring, P sub kz, kz for Kontsevich-Zaghi. I will introduce it in a few different steps. And the idea here will be we'll sort of record all the periods, and we'll only get rid of the relations we can see using geometry, ignoring what the actual integrals evaluate to. So first, let me tell you the generators. So over Q, we add the symbols x, z, n, gamma, and omega. The n really is just kind of superfluous, but I guess it's bookkeeping. So I'll include it, not to deviate too much. Where gamma is a relative homology cycle, and omega is a relative de Rham cohomology class. And x and z are Q varieties with z inside x. So one point which confused me, so I'll just talk about it very briefly. You can see here we have de Rham cohomology, and so we're looking at integrals of closed forms. Of course, you can consider integrals of non-closed forms as well. This turns out not to add anything, because you can always, by projection, reduce to the dimensions being such that you're sort of a top holomorphic form and automatically closed. So we lose nothing by insisting on working in cohomology. I'm sorry?
Is it the case that you can make z a normal closely divisible and smooth variety?
You know, I believe that's the case, but I'm so unsure about all this stuff that I'm going to leave it like I know. I've seen it written down like this, and I think does somebody else know?
So
Yes.
For the generators, you can, but it's not clear that you get the correct information.
Right.
To me, it's not clear.
I basically go by what's in Annette's book, so if it's not there, it's not going to be here. Yeah.
Question, does this include improper integrals?
Improper, like this case here?
Like an integral from zero, something that sort of maybe converges conditionally or things like that, I don't know.
Oh, I see. You're saying, for example, like this guy where I cheated and at 0, it's improper. It includes some of them because you can often get rid of them by blowing up. I don't know if it includes all of them. Yes, it does. Okay, there you go. I'm so glad you're here. I mean, I would be totally lost. Okay, so here are some generators. Now let's put in some relations. So the first relation is easy. We just want additivity in gamma and in omega. The second relation is base change. We already alluded to it in this computation here. If we have a map from x to x prime, which sends z to z prime, then the push-pull formula basically has to hold. So if we push a cycle and integrate, that should be the same as pulling back the form and integrating. F star, no. X prime, z prime, right. And this is xz. This prime's gone, this prime's gone. Great. So essentially the push-pull formula holds. And the third relation is given by Stokes' theorem. So if we integrate d of a form, it should be the same as integrating that form on the boundary. And that amounts to, if we have z inside y inside x, and omega, like class, in this relative cohomology group, then we have this relation, where we think of d omega as a member of the appropriate group, is the n minus 1. Okay, and that's all the relations. Now, normally you don't, well, I guess you don't have to do anything, but normally you also do a little bit more, which is you invert the sort of O1 element, the element 2 pi I, which I'm going to underline because I'll think of it as a member of this group. And basically what it is the integral of dx over x along the circle, which of course evaluates at 2 pi I, which is why it's called this, and we invert this guy. Okay, and that's how you define the period ring. It's very concrete. Of course, in order to actually compute what this is in any sort of reasonable sense, you have to find all the relations, hence it's hard. But just to give a definition is very clean. And the point now is that we have an evaluation map from this ring to C, which just sends each of these generators to the thing it was set up to be sent to, the integral of omega over gamma. Okay, and so now we have a conjecture due to Kontsevich and Zagier. Which says that all the relations are the ones you already see from geometry. Therefore, they're already plugged into this ring. And so you can just say that this evaluation map is injective. Now, this is stronger than the Grothendieck period conjecture. The Grothendieck period conjecture, which we'll give sort of more precisely in a minute, says, well, I don't really care if you mod out by nilpotents or things like that. And so essentially what this is saying is you only care about this up to transcendence. So you don't lose any transcendence by passing down. Transcendence. And formally speaking, it says that the kernel of EV is a minimal prime ideal. And these two are very close to being equivalent, though not equivalent, so not that close. Or at least not known to be equivalent. Oh, right, I can keep scrolling up. Oh. Okay. So I've given you this conjecture in sort of very elementary terms, so that it's hopefully very understandable. Now I'll give it to you in more complicated terms in order to make it seem like the subject's hard, and also in order to make the transition to the function field setting a little bit more natural. So in that spirit, let me say something about motives. And everything I say is due to Nori, his sort of unpublished papers, and Huber Mullerstock in their book, who actually work out a lot of this stuff. And the idea is the following. We're going to consider the following category of effective pairs over Q, whose objects are just triples x, y, n, where y inside x is a Q variety. And such that the maps, there's two different kinds. If you have a map from x to x prime, which sends y to y prime, then you record a formal map from x prime, y prime, n to x, y, n, which is supposed to be sort of a pullback map. And if we have these triples, z and y and x again, we have a boundary map from y, z, n to x, y, n plus 1. And the idea behind this category is it's supposed to sort of record for us the nth relative de Rham cohomology group. And so right away, we have this important functor from this category to Q modules, which just sends a triple x, y, n to the nth cohomology group of x relative to y with Q coefficients. And I'm not going to write where it sends these maps, but it sends these maps to sort of the obvious places. Okay. So the benefit of doing this is we will, in a minute, define the motivic Galois group, which is really the thing we're curious about. But to me, at least, in this language, you can understand what the question amounts to very simply. We're trying to understand what are the symmetries available in sort of these cohomology groups, which commute with all the maps coming from geometry. How much of a restriction does geometry place? And so in this vein, we can define this pro-algebra. I'll write as endomorphisms of Fc, which is the following. It's compatible sets of elements R sub m, where m is an object in pairs. And each R sub m is an endomorphism of the corresponding cohomology group, such that whenever you have a map phi from m to m prime, these endomorphisms commute in the appropriate sense. So if you first apply Rm, And then phi is the same as applying phi and then Rm prime. Yes.
And it's not negative.
Yes, and it's not negative. Sorry. Okay, so it's some giant thing. You're sort of looking at all of these pairs at once, and you want all endomorphisms which are compatible. And then what a Norrie motive is, the category is the same as the category of R modules. So sort of finite dimensional vector spaces with the appropriate topological restrictions. And in this way, you can see that all of these guys are naturally R modules because it acts on them sort of by the face of it, by the map to all of these endomorphism rings, morphism groups. But you have other ones, and sort of all the motives are kind of quotients of these guys. It's very similar to the kind of story you get from Hodge theory or from L-adic cohomology or anything like that. But okay, there's sort of more motives, but for the purposes of everything we're saying, you can just restrict your attention to these. You don't sort of lose much. The benefit of doing this is that we can now do is given two motives, we can define this tensor product as another motive. And this is not entirely trivial. In fact, it requires some non-trivial algebraic geometry because you have, when you tensor these two groups, you will have the Kuhn formula coming into play. And you sort of don't want the Kuhn formula. You want only that one term that you care about. And so essentially, what you can do is you can show that you can break everything up geometrically into pairs where you only have one non-zero cohomology group. And so this problem doesn't show up. Sort of massage that, and you can define these M tensor M primes. And now it turns out that this category is equivalent to a certain category of representations under the motivic Galois group. Or or I guess modules, G mod key modules. And what is this group? Well, it's those elements Rm such that Rm tensor Rm prime is naturally equal to or maps to Rm tensor M prime. So you want a compatibility with a tensor product as well. And once you have this, this actually gives you the motivic Galois group of Q.
Is it a representation of the Q point of the group or a representation of the group scheme?
Sorry, yeah, this is a group scheme. This is not Q points. So it's whatever points are just you add that coefficient group to all this stuff.
Coefficient ring.
Yes.
Okay, so this is a quasi-algebraic, pro-affine algebraic.
Yeah, so this is a pro-algebraic group. Exactly. Pro-affine algebraic group. Exactly. Okay, so that's some huge group. But now given any motive M, you can define its motivic Galois group as just the image of the big motivic Galois group in GL of the corresponding vector space of Sing M. Okay. So now we're almost ready to state the Grothendieck period conjecture, because this group sort of tells us how much symmetry we have. And now we have to find a way to write the periods in this language. And that's done in this very convenient fashion, because we defined the functor f Sing here, taking Betti cohomology, but there's many other functors here. There's many other cohomology theories. All of them give you a functor from this category. So in particular, we can look at the de Rham functor. Which sends a triple to the corresponding de Rham cohomology group. And now you can think of integration as just an isomorphism between these two functors defined over C. Because if we look at cohomology over C, then they're the same. So integration now is just this map between these guys. And what are the coordinates of this map in some basis? They're exactly the periods. And so I don't want to pick a basis, but what I can do is I can define this field over which these maps are defined. That way it's a canonical subfield of the complex numbers. It doesn't require picking any basis. And now in this language, we're ready to state, I still don't need an eraser, wow. In this language, we're ready to state the Grothendieck period conjecture. And what it says is the transcendence degree of this field is equal to the dimension of the Motivy-Galois group. It's an algebraic group. So a few remarks. Of M, thank you.
I mean, you feel you would just look at just for M itself.
For M itself, that's right. So you look at symmetries of the cohomology groups of M, which commute with all other sort of maps. Okay, so a few remarks. One is that the less than or equal to direction is easy, or easier, and known. And that's to be expected, because to get this inequality, all you got to do is produce relations amongst periods. And producing relations, you can just sort of do. Whereas to get the lower bound, what you got to do is show things are linearly independent, are algebraically independent, and that's sort of the hard part. And the other thing I want to say is, in fact, this Motivy-Galois group, even though it's defined in this rather large-looking way, this is often computable. I don't know if it's always computable. I don't know if that's true, at least. But in many cases, in particular for all one motives, you can compute this Motivy-Galois group exactly. So you can actually extract precise numbers out of this. It's not just some sort of unrelated quantity that you're supposed to be equal to. And finally, this is sort of known for one motives. I use known in quotes. I'll explain why, due to sort of a few people, but Huber-Vosholz have a book where they do this. I say known because the way I wrote it down, it's not known, because I'm doing algebraically independent. But if you were to write this down with just linear relations, which you could do because you can record polynomials by taking tensor powers, this would be known for one motives. I'm sorry?
The linear translation is known for linear relation of periods of one motive. Yes?
That's right.
Not for algebraic relations between periods of one motive.
Correct.
So now there is also a formulation in terms of the torso of isomorphism and fiber functors.
That's right.
And now the group, as far as I said, the group is not necessarily connected.
That's right.
And so you can say that the closure of the C point is an irreducible component of the top. This would be Grothendieck's conjecture.
That's right.
And the other slightly stronger conjecture is that the torso itself is irreducible over Q.
That's right. Or equivalently, the Motivy-Galois group is irreducible over Q. Because it's a torso, right? Over Q bar, sorry, over Q bar.
Or equivalently, the Motivy.
I mean, I might be screwing this up, but I think it's equivalent to the Motivy-Galois group being irreducible over Q bar, so being geometrically connected.
So but when you're over Q, the Motivy-Galois group.
Oh, yes, you're right. No. That would be if I stated it over Q bar, but I stated it over C. That's.
If you do motives over Q bar, so for algebraic
Yeah.
Q bar, then conjecture is that the Motivy-Galois group is
Okay, so before moving on, I want to explain a generalization of this conjecture. It's already very general, but there's a problem that André noticed, or potentially a problem, is that E, for example, is not a period. Probably. You know, it's very hard to show things aren't periods, but we don't expect E to be a period. In fact, it's going to follow from the conjecture that I'm about to state. And so this conjecture doesn't contain any transcendent statements about E. In particular, it doesn't include Shanuel's conjecture, which is one of the other sort of major transcendent statements, which says that e to the x is as transcendental as it could possibly be. So I'll state it in general and give a couple of examples. So if you take n complex numbers, and you assume they're q linearly independent, then the transcendence degree of all these numbers and all their exponentials is at least n. So you could obviously make it, so usually it's 2n, because for most numbers, why would there be anything? You can, of course, make it n, just by every time you add a variable, include some algebraic relation. And if you have them be q-linearly dependent, then you're not adding anything, because you get algebraic dependence here and multiplicative dependence here. But otherwise, n is the most you can get. As a brief application of how strong this is, if you take n to be 2, alpha 1 to be pi I, and alpha 2 to be 1, this implies that E and pi are algebraically independent, which is very, very far from being known. So the statement is very far from being known. But the point is that it's not included in the period conjecture, and we would like it to be, because E, in a sense, can be described by periods. In fact, E can be defined as that number such that the integral from 1 to E of dx over x is equal to 1. So how do we include that? We include it as follows. So I'll say André Grothendieck. We include it as follows. For any subfield of C, finitely generated, and any motive M over K, I only define motives over Q, but you can do the same thing over basically any field. If you look at the transcendence degree, over Q again, of K adjoined the periods of M, now you don't get equality, but it should be at least the size of the motivic Galois group of M, viewed as a K motive. So what's the idea here? Well, the idea is if you want to see stuff about E being transcendental, what you can do is work over Q adjoined E, and over Q adjoined E, now you have a period relation, a relation amongst the actual periods, which doesn't come from formal geometry. Formal geometry is not going to tell you that integral from 1 to E dx over x equals 1 E is just an arbitrary transcendental number. And so, but you pay a price. You pay a price because E is transcendental. You can sort of always adjoin a transcendental guy to get a relation amongst periods, and so you include the K inside here. And the idea is that this is, well, just like Shanuel is in a precise sense sort of the most general statement you could have about transcendentals of the exponential function, this is the most general transcendental statement you can have with respect to all the period functions. Yeah, that's a good question. Well, I mean, it's less than or equal to the transcendence degree of K plus this dimension. That would sort of be the analog, I think, but I don't know of anything stronger. By the same reasoning, if you sort of do this over K instead, you can write as many period relations as you need over K, and so you get this inequality. So then if you're over Q, it's a plus K. Yeah, I can write it down. Easy thing is that the transcendence degree over K of K adjoined the periods is at most this dimension. Okay. All right. So now that we have this, what I'd like to do is move to the function field setting, where in some ways it's more confusing because we don't have this nice Q inside C. We've got to work a bit harder. But in other ways, some objects become more familiar, like the Motivigawa group, which will essentially be a fundamental group, as we'll see. So, what is our basic setup in the function field setting? Well, so now we'll work over a base field K, which will be a finitely generated extension of C. And because K is of this form, we can think of K as the function field of some variety S over C. Of course, this is not done in a unique way, but it's not going to sort of matter. Now, if we have a variety, x naught over k, we can spread this out in the usual way to a family of x over s, possibly at the cost of shrinking s. So, for every x, we've got to shrink s a little bit more in order to get this, such that the generic point of this returns our x naught to us. Now what we do to define sort of these periods is we got to find something to integrate over, we got to find something to integrate, and we got to find something for the integral to take values in. So we have these three different jobs for us. So what we do is we fix a point P inside a ball B, inside the C points of S, some simply connected thing. And then if we pick things judiciously, then this X, which I'm going to assume for now is smooth projective, let's say smooth projective, so we don't have to worry, is going to be locally trivial. So the cohomology of X over the base is going to be trivial in a neighborhood. So this is a local system. Okay, so now we can integrate over it fiber by fiber and get something reasonable. And if we have an omega, a de Rham cohomology class in X naught, what we can do is we can spread omega out and get a relative de Rham cohomology class. Let me call this omega naught. And it spreads out to omega, which is a relative de Rham cohomology class of X over S, which is this push forward, which is not necessarily a vector bundle. We might have some bad points, but you can assume over B it's a vector bundle. And now we have a comparison theorem between them. Oh, I should. Right, let me follow protocol. We have a comparison theorem. So these are isomorphic over the field of holomorphic functions. Which holomorphic functions exactly? Let's say the sort of meromorphic germs of S over this point P. And so what is happening here exactly are these are just the coordinates of the, sorry, not the coordinates. These are just the integrals of algebraic forms fiber by fiber, where we're integrating over these locally constant sort of classes. So for an elliptic curve, you can trivialize this cohomology. You just get these two cycles, and you can integrate your form, or your algebraic de Rham cohomology class, more generally. OK, so now, as a remark, and something I'm not going to focus on, It's a little annoying that you can't just fix a point to work over, because whichever point you pick, you can find some x which behaves badly over that point, and then you're kind of in trouble. And in fact, I think mostly for this reason, Norrie wrote his stuff not for guys over C, but for guys over subfields of C, which are big enough that these guys have generic points still. So what we do to fix this is we pick P to be what we call an arc point. There's lots of ways to handle this, but essentially what it is it's a map from some small interval. Actually, you don't need it to be closed, like this. 0 to S, which is well defined up to cutting off the tail. So you just sort of want the germ of this map. So it's some germ of this, germ at 0. And we sort of use that as a base point. And it's sort of just a trick to allow us to, if we remove the risky closed varieties, you still have this guy and you can still do all the fundamental group stuff, all the fiber stuff. It all still works. You get a slightly more complicated fiber functor. The advantage is you can then actually work over C, which is of course what you actually want to do. Okay, so that's kind of a technical point which we don't need to worry about. So now what we can do is define some relevant groups. So we'll define by, sorry? Yes. Yes, the C points of S, thank you. Up here? Thank you. Oh, over here as well. Yes, that's right, the C points of S, of course. So let's define some groups. So we have the fundamental group of K, which is sort of the projective limit of the fundamental group of all of these S's. Different models, you sort of keep shrinking, removing more and more stuff, you get a bigger and bigger fundamental group. Here's some pro-discrete group. Yes, that's right, in the other direction. Thank you. And you have the motivic Galois group, again, using the same construction with Norrie motives, everything works out. There's a slight obstruction, though, which is that now we want to think of constant numbers just as trivial. So if we have a constant x over x naught over k, just base change from C, we just want to say that integral equals that number. And the geometry doesn't really see that. So what you do is you have this very convenient exact sequence. The motivic Galois group of K maps to the motivic Galois group of C. This map is surjective, in fact, with this setup. And we're only focusing on the kernel. It's called the relative motivic Galois group. So this is just a trick, or maybe not in the pejorative sense, but it's something you do in order to declare constant families as sort of having constant integrals. That's what that sees. Okay, and now the very nice fact, due to Ayub and Norrie proved this, but in, again, unpublished sort of notes, and Ayub did it separately. So you have a natural map from this fundamental group to your relative motivic Galois group. And it's not surjective, because this is pro-discrete, but it has the risky dense image. So essentially, if you're now trying to understand this quantity, the motivic Galois group of some motive M, well, you have some cohomology group. You can think of it as a local system defined on S for some reasonable S. And all you're looking at is the image of the fundamental group on that local system, on some fiber. And its Zariski closure is going to be sort of this quantity over here. So essentially, it's saying the symmetries of motives here can be detected purely from the local systems. That information is enough. And then Ayub proved the period conjecture, the transcendence degree over K. If K adjoined the period of any motive with the same definition is the dimension of this relative Galois group, which again, if you want to ignore motivic Galois groups, this is just the dimension of the image of pi1, Zariski closed. And so in this case, the theorem that I want to talk about in the last 9 minutes is essentially André's generalization. If you have K inside L inside the sort of analytic germ closure of K, so this is some finitely generated extension, you have a motive over L, then the transcendence degree over K of L adjoint the periods of M is at least the dimension of this relative Galois group. Okay, these are very hard to just look at and understand what one says, what the other says, so forth. Let me give you an example. For those familiar, this is essentially a very general Ax-Lindemann statement, and this is a very general Ax-Shanuel statement. So an example of a statement that's sort of accessible via this statement, but not this one, is if you look at the functions x, log x, and e to the x, these are algebraically independent. Now, this is not the most impressive looking statement. I bet people here could prove it, given enough time. But this is an example of a statement which follows from here, but it doesn't follow from here. Because essentially, what this statement lets you do is take any number of algebraic functions you want, take their logs, and then understand that field, but you can only take logs sort of once. Whereas this allows you to iterate your period functions as often as you want. That's kind of the, practically speaking, that's the difference. Okay, in the last, now 7 minutes, let me talk about the proof of this. And it's kind of a very, to me, it's a very nice coincidence that there's been this field of unlikely intersections, and within it, you have sort of the functional transcendence side, and it's all about if you intersect things which are algebraic in different structures, then the dimension of that intersection should be what you expect, and no bigger. And otherwise, you call it unlikely, and the gist is you want to prove if something's unlikely, it's for a good reason. So it's all about studying intersections of loci like that. It was started, actually, with the Ax-Shanuel theorem. James X formulated and proved an analog of Shanuel's theorem, Shanuel's conjecture, in the function field case. And then it was sort of generalized to Shimura varieties because of the André Grothendieck conjecture, and then to Hodge theory and several other settings. It sort of all leads up to the period conjecture, which encompasses all of that stuff, which I think is very nice. So let me state the Ax-Shanuel theorem in a way that I rarely see it stated, but to me is much more natural. Because usually when you write this theorem, there's an annoying rank term of partial derivatives. And everybody always asks, why is that term there? And you're sort of like, well, it's necessary, trust me. But you can formulate it without that term, which is, I think, much cleaner. So take n elements, which are power series in R variables. Take them to be Q linearly independent mod C. Then the transcendence degree over the field C adjoined these variables, the rational function field, of the f's and their exponentials is at least R. Is at least n, excuse me. So I view this theorem as, again, very nice because you have this at the base, which you sort of should. You're working over a function field, and there's no sort of extra terms. The annoying dimension term you usually see is already built into this setup by working over this field. So Ax formulated this statement, which has a very clean, I'll write it here, geometric formulation in the following way. If you look at x from c to the n to c star to the n as a coordinate-wise exponentiation, and you let j be the graph, gamma be the graph of x, and then you let u be in gamma such that the image of u is a risky dense, is not contained in an affine linear space. Then the dimension of the Zariski closure of U is the dimension of U plus n, at least the dimension of U plus n. So you can formulate it purely about these sort of weird sets and their intersections with algebraic varieties. Now, it turns out the Grothendieck period conjecture has a similar formulation. I think I have just enough time to state. So I'll go rather quickly, I'm sorry. So on S, let V with a connection be a flat vector bundle. U is an arbitrary sort of analytic thing inside here. So let V with this connection be a flat vector bundle. And let B in S be some disk. Be simply connected. And now, because we're flat, if we fix a point in B, we have a section from B to the total space of Hom from V to V naught, which is just another vector bundle over B. And this section is basically flat continuation, which you can locally do. So we have this natural section, and it turns out that the Grothendieck period conjecture is exactly so the André generalization of the Grothendieck period conjecture is exactly the same as the sort of natural X-Shanuel statement for the graph of this B, that things intersected in the correct dimension. I'm not going to write down the exact sort of formula. It's a little bit annoying, but it's sort of very natural, and these two end up being equivalent. And so just a word about proofs. There are sort of two proofs we give. One builds on work of Chu, plus a bunch of other people, Klingler, Eriksov, Umo, Yafaev, myself, Jonathan Pila, Gavin Mock, Axe, and Shanuel. And this follows the sort of strategy that's been developed in the last decade or so, the Pila-Zanier strategy. This uses O-minimality, the point counting work of Pila-Wilke, and the monodromy information you get from André Grothendieck. But there's another proof you can give that was given recently by Blaske, Sons, Freitag, Naglu, want to make sure I get these names right, and Callas, which only uses the André Grothendieck. They have this beautiful new approach to it, using essentially differential geometry, and they phrase it using the language of G bundles, which allows sort of for a much simpler treatment of at least the cases that come up. Okay, I'll stop here. Thank you very much for your attention.